Hi, this is Professor Fernandez working on class notes B in lesson 14. In this example, we want to take the third order ODE from the previous example and express it in the form 14.7 and then classify the system according to the definition above. So let me just scroll up and go through this definition really quickly. So first, 14.7 is a system of this form. So, we'll get there. Let me talk about what's above it first. So this is a definition that is defining what a system of n first order ODEs, so SN FOD, looks like. It has the following form. So on the left hand side, you have derivatives, first derivatives of a bunch of unknown functions, x1, x2, all the way to xn. On the right hand side, this notation means that you have a function of possibly t, possibly x1, all the way down to possibly xn. Right, so what's an example? Maybe like t squared plus x1 plus x7 or something, right? So that's a function of t and x1 and x7. So a system in SN FOD of n first order ODEs could look very complicated, right? These right-hand side functions could be very complicated. As examples, lots of exponentials, logarithms, trigonometric functions, who knows? So what are simpler versions of these systems? Well, we call such systems linear. Notice the L here, SN fold. If the right-hand sides, these F's, take on a very simple form, namely a linear form. So there's some function of t times x1 plus maybe things that look kind of like it all the way down to some function of t times xn, and then plus something that does not have any x's in it. So if every one of the f functions on this right-hand side has that form, then this system is linear. So SN fold. And you can kind of see where the linearity comes from because the unknown variables appear on the right-hand side only in a linear fashion, right? There's no squares, there's no sign of these variables. Those would be like non-linearities. Okay, so then we can see what it says down here. Such systems can be written in the form, this is the 14.7, right? So if you look at this, let me highlight it better. If you look at this part, we've now seen this various times in the course. This is exactly the matrix A11 through A1n, AN1 through ANn, multiplied by the vector x1 down to xn, which in more compact form is the matrix A times vector x. Okay, so all I'm doing down here is to remind you that this matrix A, its entries may be functions of t. What would that look like? Here's an example of a matrix whose entries are functions of t. Okay, so that's kind of a new quantity, and we won't really deal with this very often, but I'll just mention that if you give me a t value, I can write down different numbers that will make their way into this matrix. For example, if t equals 1, then this matrix would be 1, 1, 1, and then sine of 1, whatever that is. If t equals pi, this matrix will be pi squared, pi, 1 over pi, and then sine of pi, which is 0. Okay, so that explains this notation over here with the a of t. So what is left over? Well, so on the right-hand side of the system that we have been just working with in this definition, in the linear case, we have all of these g of t's, right? And these don't have the x's in them. So that explains why they get put just in their own vector without any x's. So, if we're thinking of what we've done in the course before, and we look at this definition, this matrix compact form in that light, this looks kind of like a non-homogeneous term. Indeed, if g of t is non-zero, we call the system non-homogeneous. If g of t is 0, then we call the system homogeneous. And then this matrix A of t, if it doesn't depend on t, if all of these entries in the matrix are numbers, then they're constants, right? So in that case, we call the system a constant coefficient system of n first order linear differential equations, a CCSN fold. Okay, so we will spend a lot of time in the course in the next few lessons studying this CCSN-fold case in the homogeneous case, where again g of t is 0. So it's going to look like that. All right. Okay, so now we reviewed this definition and we've reviewed 14.7. So let's scroll down to the example and see if we can finish that one. So this example says, basically use the previous definition to put this ODE into that form, the matrix form, and then classify the system. So I actually did this in the previous video, so I'm going to say see video for class notes A. I did this at the end of that video, and this is what we got. All right, so this is the matrix form. Here's x dot equals A. In this case, A is not a function of t. X dot equals AX. And then plus, this is the g of t function. Okay? So if we see it in this way, first of all, it is a system of 3 first-order linear differential equations. All right. So the 3 comes from the fact that there are just 3 x's in here, 1, 2, 3. The linear comes from the fact that it has exactly this form. Okay. And then we look at the A matrix, and the A matrix does not have any t's in it, right? They're all numbers. So it's a constant coefficient system of 3 first-order linear differential equations. And then finally, we'll look at the g. And the g is not the 0 vector, right? There is a g. This e to the t down here makes it a not the 0 vector. So this makes it a non-homogeneous system. Okay, and that's the classification.